Let's talk about exponential functions. All right, exponential function means something like 3 to the power x, or 10 to the power x, or 5 to the power x squared plus 2x. That kind of a thing. That's called an exponential function. It's when the x is in the exponent. All right. When the x is in the exponent, that's called an exponential function. And these are different from things like we've talked about before. So when I say exponential function, I mean something like that. I do not mean something like x to the power 3. All right, that's there's an exponent there, but this is not called an exponential function. This is a polynomial, right? An exponential function is what it's called when the x is inside the exponent. I want to talk about derivatives of these kinds of functions. We have talked at length about derivatives of this kind of a thing. The derivative is very easy to do. There's the power rule. Derivative here is 3x squared. We know the rule for that. What about these? Turns out for exponential functions, there is a completely different set of rules that you need to use to take the derivative. You cannot use the power rule on this. The power rule works when x is on the bottom. When x is up here, you do not bring the exponent down and then decrease by 1. You don't do that when the x is in the exponent. All right, that's what we're going to talk about this time. How do you find the derivative of an exponential function like that? First, just a little review about what these things are. Generally speaking, an exponential function looks like this: a to the power x, where a is some number. I'm going to say actually positive number. If the a is negative, you get some very weird stuff going on. You can get imaginary numbers, and I'm not into that, at least not right now. In my own personal life, I kind of am into that, but here I'm going to just talk about a to the power x, where a is some positive number. That number is called the base of the exponential function. The graph looks like something like this. This is the graph of a to the power x, where this goes through the y-axis. The y-intercept is 1. That's because if you plug in x equals 0 here, you get a to the power 0, and anything to the power 0 equals 1. And so the graph of this goes through 1 when x equals 0. And otherwise it looks like this. If you don't believe me, you can just plug into your calculator, 2 to the power x. You will see it looks like this. It depends on what the a is, what number that is down here makes the graph look different. How they look different is if the a is a bigger number, this thing looks steeper. So if I were to change the a and make it bigger, then the graph would look more like this. This is, I'll just say, a bigger a would be steeper like this, or even, steeper like that. So things in this range would have, that's what it would look like when the a was bigger. If the a is smaller, it looks, still has the same basic shape, but it's like, shallower, less steep like this. This is like a smaller a. All right, this is what exponential functions look like when you graph them. They start real small, they go through 1, and then they shoot up rather quickly. Now this one is going up rather slowly, but eventually if you go out far enough, this thing is going to go way up just like these ones are over here. All right, this is what an exponential function looks like. I want to talk about the derivative of an exponential function. It turns out you can get a fairly good idea of what the derivative is of one of these just by looking at the graph. So I hope you remember we talked we spent at least a day talking about how do you find the derivative graphically, like you look at a graph of something and you draw a graph of the derivative. I want to try and do that with one of these. So I'm going to draw it again. All right, let's say this is the graph of a to the power x. Right underneath it, I'm going to try to draw the derivative of a to the power x. I hope you remember how to do this. The first thing you should do is look at the original graph and try to find any points where the derivative equals 0. That would be, if you see these kind of things, that would be points like this. These are points where the derivative equals 0. Actually, I don't see any of those things here, right? When you look at this, there are no points like that when the derivative equals 0. You might say there's kind of almost a point over here. The slope gets almost flat horizontal, but it doesn't. I hope you understand when I draw this picture, I mean that this thing just like approaches the x-axis like an asymptote as it goes off to the left. So the slope never actually reaches 0, although the slope as you go off to the left approaches 0. That means when I draw this, there are no points when the derivative actually crosses the x-axis. But as you go off to the left, the derivative, whatever it is, approaches 0 as you go off to the left. So that means when I draw this picture, there's kind of two choices. Whatever I draw here, it must approach 0 as you go to the left. So either it's something that looks like that, as an asymptote it comes over that's this way, or it's something which looks like that, right? Either way, it has to approach 0 as it comes off to the left here. Although I don't know if it does so from above or from down below. That would have to do with is the derivative positive or negative, right? That's how you know, like, does it go up here or does it go down here? That, you look up here and you ask yourself, is the derivative positive or negative? Well, is it? Look up here. Yeah, it is positive. In fact, it is positive all the way throughout here, and it is becoming increasingly more positive over here. So, when I draw the derivative, it's not this one down there, right? It's the positive one, not the negative one. And what I just said is, it's always positive, and it becomes increasingly more positive as you go over to the right. What that looks like on a picture is this. Always positive and becoming increasingly more positive. That means it just is going to keep going up forever. Okay? This is what the derivative of a to the x looks like. This is the derivative of a to the power x. I want to ask ourselves, when you look at this, does that look like anything? Like, really, I want a formula for this, right? So can you look at this picture and become inspired to guess what the formula for the derivative is? Does this graph look like any function that you know? Does it look like any function that you've ever seen before? Think about that for a moment. I think it does look like something I recognize. In fact, it looks the same as that, doesn't it? I'm not saying this derivative is exactly the same as this, but they look very similar indeed. So let me just say this derivative looks like a to the x again, right? This shouldn't convince you that it really is the same as a to the x, but at least the picture of the derivative looks an awful lot like a to the x. It turns out, and I hope you will take my word for this, although you can look it up in the textbook if you want a more detailed argument for this. It turns out the derivative of a to the x is actually almost the same as a to the x. It turns out not quite the same. Here's the real formula. The real formula for the derivative of a to the x, it is a to the x times ln of a. This ln is the natural logarithm. There's a button on your calculator that says ln. That's what that means. If you don't know what logarithms are, you have a bad experience with logarithms in your youth, don't worry about it. It's not a big deal, especially what we're going to do this time. It doesn't matter. All you need to know really is that the ln is a function, it's a button on your calculator that you can plug into. And since a in this formula, a is a number. Remember I said a is just some specific positive number. This part will always just be some number. If a was 5, this is the natural log of 5. You plug that into your calculator. It's just some weird number. All right? So this is the formula for the derivative of a to the power x. This formula you will need to have memorized, unfortunately. We're going to use it an awful lot, though, so hopefully it will just come naturally to you. Let's just do some examples here. Here's a simple example. There's really almost nothing to this. What is the derivative of 2 to the power x? Don't try and think too hard about this. All you got to do is plug into the formula here. I'm using this formula. The a is 2, so I get 2 to the power x times ln of 2. And what is ln of 2? Well, like I said before, this is just some number. If you want to know what that number is, you can plug it into your calculator. You know, type that into your calculator, you get some kind of answer. So this is just 2 to the x times some number. All right? I don't typically care what this exactly that number is. If you want to write it out in decimals or whatever, I don't care about that. This is the derivative of 2 to the power x. And really anything to the power x is no different, right? The derivative of 10 to the x is 10 to the x times natural log of 10. and so on. There's basically nothing to this. You just need to know the formula. All right. What about, there's one very special number. I hope that you've at least heard of logarithms before. And if you have heard of the natural logarithm, you probably have also heard of the number e. The number e is a very special number. And this is something actually that we're going to be talking quite a bit about in this class. What about this special function e to the power x? E is a special number, 2.8 something something. It's kind of like pi. It has digits, decimals that go on forever without repeating. What's so great about e? The great thing about e is this. The natural log of e equals 1. Again, if you don't believe me, you can check this on your calculator. That's the fact about e that makes e interesting. Basically, that is why e is a special number, because the natural log of e, the answer is 1. Anyway, what do you get then when you take the derivative of e to the x? You use this formula. You get e to the x times natural log of e. But I just said natural log of e equals 1. And so this part is just 1. The answer is just e to the x times 1, which is e to the x. So this actually gives you another formula for derivatives of exponential functions. Would you mind if I try to squeeze it in right in here? I hope you don't mind. Derivative of e to the power x. So here a can be any number, right? Here e, I'm talking about e. There's a specific number called e. That's the special number. And the answer is just e to the x. All right? Put that in a box of formulas to memorize. This is a pretty great formula. This is like the greatest formula for a derivative that there is. The derivative of e to the x is just e to the x again. In fact, little known fact, impress your friends, e to the x is the only function like this. Actually, any constant times e to the x is the only function which is equal to its own derivative, is e to the x. When people ask you what's so great about e to the x, you can tell them this. The derivative of e to the x is e to the x, and that's the only function which has that property. All right? These I would consider to be some simple examples. Let's just try a few examples of derivatives of exponential functions that are not just so simple as just plug into the formula. All right, I want to do some that aren't just simply plugging into the formula. Here's a fairly easy one. What about derivative of 8 times 2 to the x? All right? 8 times 2 to the x. First of all, you may be wondering to yourself, isn't that the same as 16 to the x? Because 8 times 2 is 16? No, it's not the same. Because of the order of operations, all right? You do exponents first. So when I write it this way, what I mean is this function is 2 to the power x. Whatever the answer of that is, you multiply by 8. That is different from 16 to the power x. They're not the same. So this is really something different from just 16 to the power x. How do you handle this? How do you take the derivative? You know, the only difference between this, so 2 to the x looks like a to the x, right? I'm going to use this formula with a equals 2. What do I do about the 8, though? The answer is you don't really have to do anything about the 8 because 8 is a constant multiple of this function. Remember, when you have a constant as a coefficient in front of a function when you're taking the derivative, you can basically ignore that constant and just leave it in your answer. So this is the same as 8 times whatever the derivative of 2 to the x is, all right? Now, you don't really have to write this step. You can more or less keep this just sort of in your head. When I take the derivative of 8 times 2 to the x, the 8 just stays in front as a coefficient, and then I do whatever the derivative of 2 to the x is. So this becomes 8 times whatever is the derivative of 2 to the x, it's that. 2 to the x times natural log of 2. All right? Let's try another one. How about derivative of x times e to the x? All right? Now, over here, when I multiplied by 8, that was very simple to handle. You just sort of leave the 8 alone and you take the derivative of the other part. What about multiplying by x? Can I just leave this x alone and just do the derivative of e to the x? The answer is no. This thing about leave the 8 alone, that only works because 8 is just a constant. If it has some x's in it, you can't do that. You got to ask yourself, how do I handle the derivative of two things multiplied together? How do you handle the derivative of a product? I hope you remember. We got rules for that kind of thing. You use the product rule. All right, so right here, I'm going to do the product rule. I go the first thing, which is x, times the derivative of the second part. My two parts here are x and e to the power x, right? What is the derivative of the second part? Derivative of e to the x, remember your formula, is e to the x. So I put e to the x right there. Now it looks like I didn't do anything here. I actually did do something. I took the derivative. It just so happens that the answer is the same as what we started with. This is only half of the product rule, right? I go the first part times the derivative of the second part, and then plus the second part, e to the x, times derivative of the x is 1. And that's the answer for this derivative. Alrighty? I got two more. How do you like that? Derivative of 10 to the power x squared plus 3x. Alright? How are we going to do this? Now, you should, think to yourself, well, this is an exponential function, and the base is 10. So it looks kind of like this, where it's a equals 10, right? The difference is, instead of just x in this formula, I have something else up there, all right? You got to ask yourself, which of my rules am I going to use? I'll tell you what it's not. It's not, well, okay, obviously, it's not the quotient rule because there's no quotients in there. It's also not the product rule. That's because there's no multiplications in here. What you have here is not 10 times that stuff. It's 10 to the power of that stuff. This is not a multiplication. It's not a product. So you should not use the product rule. What's left is the chain rule. Is this chain rule is used when you have one thing stuck inside of another thing. Is this one of those? Actually, it is one of those. What we have here is the exponential function with base 10, and then there's another thing up here. Instead of, like I said before, it's not just x up there. What I have is some other function stuck up there. This is the classic situation where you use the chain rule. So let's use the chain rule. What's it going to be? You take the derivative of the outer function with the same thing on the inside, and then you multiply by the derivative of the inside. So what is the outer function? The outer function is the exponential thing, 10 to the power whatever. So I'm going to use this rule for the outside function where a is 10, and instead of x I have that stuff. So I'm going to go, the answer here should say a to the x times log of a. A is 10. You leave the same thing on the inside when you do the chain rule. It looks like this, all right? What I've done is taken the derivative of the exponential part, leaving the same thing on the inside. This is what you do for the chain rule. You take the derivative of the outer function, leaving the same thing on the inside. So I use the formula here for the derivative of the exponential function with base 10. I leave the same thing on the inside. And then, continuing the chain rule says, now you multiply by the derivative of the inside. And so I multiply by the derivative of x squared plus 3x. It is 2x plus 3. And that's the answer. All right, this is the chain rule. A little tricky, maybe. I don't know. It's the chain rule. Make sure you got those parentheses, haters. You need those parentheses in order to distribute properly. Okay, one more. Let's do one more. How about derivative of 1.1 to the power 5x squared? This is not really harder. Actually, it's a little bit easier than the previous one. It just looks weird because it's got this strange number down there. It doesn't really matter though. We do exactly the same thing. It's a chain rule again. We have an exponential function with base 1.1, which is strange, but it doesn't really matter. And on the inside is 5x squared. And so I use this formula up top, and I'm going to use the chain rule. So first of all, doing the derivative of the exponential part gives me 1.1 to the power 5x squared times the natural log of 1.1. All right? That's the derivative of the outside function, the exponential function. Then, because I'm doing the chain rule, I got to multiply by the derivative of the inside. And what is the derivative of 5x squared? It is 10x. And that's the answer. That's how we do it.